Thanks, Gareth. Thanks for the introduction. Yeah, let me start by giving a quick introduction of myself. I'm Aart Goossens. I'm a freelance sports data engineer. I have a background in human movement sciences, so yeah, exercise physiology. After my studies, I went to work first as a web developer and later as a data engineer. And at the moment, I'm combining my background in exercise physiology with data engineering as a sports data engineer. I'm explicitly not calling myself a data scientist. What I'm doing is I'm helping organizations, companies that have like sports data engineering tasks with these tasks, and also give them some domain knowledge from the world of specifically endurance sports like cycling, triathlon, rowing, running, sports like that. Yeah, so talking about these sports, the sports that have my expertise, I looked at the people that registered for this meetup, and I think that most of you have, or at least a big chunk of the attendees of this meetup see this picture as the pinnacle of sports performance. I'm afraid to say that my talk will be more about this. Okay, maybe not this guy, this middle-aged man in a light rabbit, more like this. But I'm hoping that even the diehard soccer fans that are here in this virtual meetup, I can show them in this presentation that in cycling there's also very interesting data and some very interesting data challenges to solve. With that, let's get started with my talk. So the title of my talk was Exploration of a Public Data Set of Endurance Activities. Actually, a more specific, accurate title would be Exploration of Golden Cheetah OpenData, a public data set with a lot of bike rides, because that's what it basically comes down to. I cut my talk in three parts. I'll start with a quick introduction to cycling data. So for people that are not too familiar with data analysis in endurance sports and cycling in general, this will help as a introduction, a quick introduction. And for those that are familiar, it might act as a refresher. After that, I will go to the actual exploration of the Golden Cheetah OpenData set, and I'll finish off with a small data science-y project I'm doing with this data to give an example of what challenges you can solve using a public data set like this Golden Cheetah OpenData set. Yeah, so let's get started with this intro to cycling data. Data collection in cycling is mainly the main bit. Almost all of the data that's collected in cycling is collected during training rides or races. So cyclists they have a bike computer on their bike, and they wear a heart rate monitor. They maybe even have a power meter on their bike, speed sensor, cadence sensor. Maybe they even collect some cycling, like some pedaling technique, temperature. And this data is so this is an example list of this data. This data is typically collected on bike computers, sampled at 1 Hertz. Some bike computers try to do it differently, which is a hassle for people like me to standardize that. And then after a ride, a training or a race, these data are saved in the bike computer as a for example a fit file, or synced to any of the training platforms that are available. So quick introduction to some of the training platforms that are available for endurance sports. The top row, those are the three, I'd say the three biggest one. Strava is not so much targeting data analysis. Well, it is also, but they also have a big social component. And Today's Plan and Training Peaks are targeting competitive athletes, endurance athletes, and also specifically those who have a coach, who are working with a coach to train. Yeah, the bottom ones are three ones that I wanted to give a quick shout out because I find them very interesting. The first one is interval.icu, which is a relatively new one. but I really like the simplicity, but also the number of features that this platform has. I think they will be a big competitor for the big three up top in the coming years. Golden Cheetah is an open source desktop application, so it's the only one in this list that's not a platform in the cloud. It's Golden Cheetah is a desktop application. It's developed completely open source. And the data that we were going to look at today, as the name might suggest, is coming from this application, and I'll talk about that in a bit. And the last one that I wanted to give a shout out to is HumanGo. It's a US-based startup that I work with, and they're developing a training platform for endurance athletes that provides adaptive training plans for these athletes. It's a really exciting platform to work with. So Golden Cheetah OpenData. So as I just said, this Golden Cheetah desktop application is open source, can be downloaded by everyone, used by everyone. And I think it was in 2016, somewhere in 2016, the developers of this application implemented a feature that asked the users if they were willing to share their data, their data from their rides or their runs or their swims in a public data set, in the Golden Cheetah OpenData set. And a lot of people did that over the past years. Yeah, so these data is shared by users with their consent. The data is anonymized. Yeah, I think so. Names and birthdays, GPS data is stripped from the data and then uploaded to AWS S3 bucket and made available for everyone. At the moment, I've last checked it last week. There are over 6,000 athletes in this data set with well over 0.5 terabyte of data and over 2.5 million activities, which can be rides, runs, swims, or any kind of data that is stored in Golden Cheetah, or that was stored in Golden Cheetah. Yeah, so to give a quick overview of what the data looks like in this open data set, I'll make this a bit bigger for you to see. So for every athlete, there's a big JSON file that contains some generic information about. Yeah, so if you look at the top, it shows a year of birth. In this case, someone entered that wrong. Gender and an athlete ID, and then for every ride that this athlete has stored in Golden Cheetah, there's some additional metadata like sport, which data is available, the date, of course, but a lot more metrics like that. And then next to this JSON with metadata of the athlete, all the separate activities, or separate rides are stored are available as a CSV file with like this. So there's a seconds column that of course contains the time step, and then other columns with the available data for each activity. Yeah, with that, it's time. It's demo time. I get back. I'll switch to my laptop. Yeah, I deployed an application to explore this data here. I'll leave this URL open for you to copy it if you want, but I'll join it after the presentation as well. It's a dataset application, and dataset is a framework that is basically a front end on top of an SQLite, a SQLite database. I think it's really cool technology to make data like this available and browsable, and yeah, the ease of which you can then deploy something like this and make it available for everyone is, I think it's really attracting. So if you haven't heard about dataset before, please go check it out and try to build some application with that as well. Yeah, so if you go to this URL, it shows you some explanations about the data that's in the database. The main thing is here at the bottom. There are two tables in this data set, this data explorer that I developed. There's the athletes table that we'll take a look at first. So if you scroll down, you'll see basically a table structure with a number of columns, an athlete ID, a gender, year of birth. So the precise birth date is pseudonymized, but the year of birth, which is very useful information to do some analyses, is still maintained. So it's nice to have that in the data. And then there's a URL to the metadata, this JSON file, and a URL to the zip file with all the CSVs that I just showed. So this is one of the tables, and then in dataset you can actually write SQL queries to explore this data. So let's start with a very simple one. So the one that we have now that's shown here results in the table below. So that basically shows all the columns from this dataset, limits, orders them by row ID, and limits to a number of 101 lines. But let's say that we want to explore how many athletes there are for each gender. Then we can do something like this. This is just don't be scared by what I'm doing now. It's just showing that you can write raw SQL queries in this dataset application. And let me check. So order by, what are we going to order by two? Two, and then we're going to, this should do it. So we have a total gender count of 280 females and well over 6,000 males in this database. So this is just a quick example of what you can, how you can explore these data. And then let's go to the other table in this data explorer, which is the rights one, which I think is actually the more interesting one. Yeah, so we'll start with a quick overview of the data. So you can see some columns here. There's a date column, which is of course the date of the right that happened in sport. The data. And the data column contains a letter for each data type that is available. And at the homepage of the Data Explorer, I provided a list with the translations for these letters. So, for example, P stands for power. So if you go back to here and then look for a right that has power. Okay, the first ones don't have that. We can try to look for that. So if you go here and select the column data and find the ones that contain the letter P, then we'll find, of course, the ones that then we'll find all the rights that have power. Okay. Yeah, let me think. On the homepage, I added some example queries that you can start with. So I think there are some interesting ones there, but you can also use these queries. For example, let me check, which is an interesting one. Yeah, total right count per athlete might be an interesting one. So this query will count the number of rights for each athlete and sort them by this. So the top one with this athlete ID has a count of a bit over 10,000 rights, which really is a lot. And but there are a lot with multiple thousands of rights in there. So I think this is a very interesting. It is a very interesting and big data set to work with. One thing to note is that it is crowdsourced data. So the data is not cleaned or the data is not checked or cleaned before or after it is uploaded. So that is something you have to work with. And one way to look at that is if we are going to if we're looking at the sport types. So the sport column. Let me check from rights group by one order by two. Yeah, I think this should work. Yeah, so this is the sport column, and then showing each occurrence of each value, and then sorted by these values. So there are a lot of bike rides, almost 1.8 million, if I'm correct. Yeah, also a lot of runs and a lot of swims. If you scroll down, it also contains sports like road, which probably means road cycling. And then if you go further down, there's some roller, which I think is a German sport type, cycle, cyclismo. So there's some, yeah, there's some noise in the data, definitely. So again, it's crowdsourced data, so you have to be aware of that and take that into account when you're doing analysis on this. Yeah, so one final example query that I wanted to show before I go to the to show what we can actually do with this data. This query, a more complex query and with a nested query in there, it shows the for each athlete the rides count with power, so the number of rides that have power data, and then the percentage of total the percentage of total rides that have power. And why I did this is because I want to do some analysis on power data, and for this I want to have an athlete with the highest or at least a high percentage of power data in their activities. And I think in the end I ended up with this athlete because I think all these ones were uploaded later. They were uploaded after I started this project. So the data that you will be seeing after this in some analysis is coming from this athlete ID, which has almost 97% power availability in his or her rights. I don't actually know the gender of this athlete. With that, let's go back to the presentation. So how can we use this data? Why is it interesting to have this data? And I think I mentioned this at the start of my talk. So all this data that we collect from, for example, cyclists, but I think the same applies to any endurance athlete or any endurance sport, is that we're trying to monitor fitness. And fitness is a bit of a I'm not sure, I wouldn't say that it is not well defined, but I think there are a lot of definitions, and I'm keeping it explicitly vague for the sake of this talk. What I sort of mean by this is fitness is sort of is equal to performance, but it also includes fatigue. So it's more of a container term to use here. So this data that we just saw, we can use it to monitor fitness. Why is fitness so important? As a disclaimer, this is the chart that I created here is not based on any data, not any science. It's a gross oversimplification, but I think it helps to understand for people that are not necessarily familiar with cycling why fitness is so important. So let's have the example of football. Of course, fitness is important as well. The soccer players, the football players, they need to have a certain fitness to run across these fields. But tactics are also very important, as we saw in the previous talk. For cycling, that's less the case. Tactics are for some types of bike races, those are tactics are important, but fitness is by far the most important thing. And especially if you look at so again, this is not based on any scientific data, but I think for one-day road races, tactics play a big part. So, for example, Ronde van Vlaanderen and Brabantspel just happened, and tactics play a big role there. But for multi-stage races like the Tour de France or especially time trials or cyclocross racing, fitness is basically all that matters. It's tactics don't play a big role there anymore. So that's why measuring fitness is important. But measuring fitness is also hard. I think the reasons for this can be boiled down to two reasons. One of those is that test selection is hard. It's hard to determine which test gives the results you want for your athlete, for the type of race you're training for. So let's say that you put an athlete on in a laboratory environment on a bike and put him on this VO2 max, these VO2 sensors on his mouth, and then measure his VO2 max using a specific protocol. But then what does that tell you about how we will perform on a 20-kilometer or 100-kilometer time trial, or what will that tell you about how we will perform in the rain, in the cold? So test selection is a big factor that makes monitoring fitness hard, but also that doing any maximal test to measure fitness or performance or whatever you want to call it, it induces fatigue, and it affects and sometimes even screws up your training schedule for this athlete. And this second bit is what I'm trying to solve, or so the small data sciencey project that I mentioned in the beginning, this basically tries to tackle this second factor. There are multiple ways to look at this problem. One of the ways to measure fitness without inducing fatigue is, for example, looking at resting heart rate of an athlete or heart rate variability. But there are many more ways to do that, and one of those is looking at mean maximal power curves, MMP curves, the term I think I mentioned it at the start of my talk. So what are these MMP curves? They're defined as, and I think I realized that this might be a difficult sentence to understand. So for every possible duration t, the maximal mean power, where t is less or equal than the total duration of the activity. So it basically means that for every duration within an activity, you take the best power, the best power and value. To clarify that a bit more, let's look at this workout that I created. It's a very not so complex workout. It starts with a warming up of 2 minutes at 100 watts, and then it does 3 high intensity intervals at 300 watts with 1 minute rest in between, and then it ends with two minutes at 100 watts as a cooling down. Let's put it like that. So then how does the mean maximal power for this workout look like? It looks like this, so the plot on the right. So if we look at it, so the x-axis on the left plot of the workout, it's time, and on the right one, it's duration. So it's slightly different. Basically says that if you look at here at 1 minute, 300 watt tells you that during this workout, the athlete had a maximum 1 minute average power of 300 watts. And if you look here at 2 minutes, means that during this workout, the athlete had a maximum 2 minute average power of 200 watts, and so forth. So for 3 minutes, it's about, let's say 233, something like that. And for 5 minutes, it's just a bit over 200 watts. I hope this explains the concept of this mean max power a bit to you. It helps understand the rest of this presentation. So this is of course.
Alex, maybe just a quick question that kind of came through, just to make sure we're on the same page.
Sure.
So in the data set that you get, if I understood correctly, you rely on knowing the training schedule, right? So you, in that graph on the left, you have, you know that there's low power, and then you have an intense peak and then low. Is that data captured in the Golden Cheetah framework, that you know what people are supposed to be doing, or do you only see what's on the right-hand side and then you have to deduce, oh, this was a specific training schedule that someone was using?
Yeah, so I think my next slide will explain that. So the workout that I just showed you was like a theoretical workout, and could be part of a training plan. But the data that we actually use to calculate these mean maximal power curves is the actual data from a bike ride. So for this to work, the athlete needs to have a power meter. But then if this power is recorded during a workout, data like this will be recorded, and this data can then be used to calculate a mean max power curve for this ride. So this what I showed here is a theoretical example to explain the concept of mean max power, and the actual data that we use for our analyses is built on these actual bike rides. Does that explain the question?
Yeah, very good, very good. Thank you.
Okay, sure, no problem. Okay, so yeah, so this is how data from power data from an actual bike ride looks like. So it's a bit more a bit more fluctuating than my theoretical example. And the mean max power curve for a ride like this looks a bit like this, which you could say is a bit less interesting in this case. One way to get a bit more knowledge out of mean max power curve from a single workout is to not use a linear x-axis, but a log scale. So then it's a bit more easy to both see detail at shorter durations, but also at longer durations. So I think in this case, let me make it a bit bigger. In this case, it's well, let's say that it's quite good to see that at the sort of 10-minute mark, I'd say, and there's a big drop off in data, which I suspect corresponds to this interval. And then, yeah, there's, well, the log scale helps to get a bit more detail compared to if you just use this linear axis. And I will use this log scale throughout the rest of the talk, which is not a lot of time remaining, so I'll speed up a bit. Yeah, so how can we use this MMP for monitoring fitness? And one way to do that is just record MMP values for a number of, I'll put myself in view again, to record these MMP values for a number of durations. So in this study, they did that for 5, 10, 30 seconds, 1, 5, 10, 20, 60, 120, and 180 minutes, and then track those MMPs, so these best duration times over time. And so this is a very typical way how that's done. This study of Peter Leo does a similar thing, but then combines training and racing data. But there's a different way to do this, and that is using power duration models. And these models basically, what they do is get these MMP data, so the gray dots in this plot, and try to plot a model over this. And there are a lot of quite a lot of models that are available for this. They all rely on, in some way, form of way, on critical power and W prime balance. So there's the 2-parameter critical power model, there's the 3-parameter critical power model, there's the exponential critical power model. But the one that I was interested on, and the reason I start this small project is a model that was published, I think it was last year. Do you see a year? Yeah, except that February 2020, published by Michael Puchowicz, and it's called the Omni Power Duration model. Oh, that's a mouthful. Okay. So how do we apply this model? What I basically did is grab a big bucket of data, and that's where the Golden Cheetah OpenData set comes in. Then calculate the MMP curves for each of these rides. Calculate the max value for each duration. So that's the black dots here, and then fit the model through these maximum values. This yields this yields quite good results. You can see that the model sort of okay-ish follows the maximum power curves. There's an issue with fitting your model to data like this, and that is this disclaimer that the MMP data is above all a measure of what has been done and not necessarily of performance. So if you take a big bucket of bike ride data, this data will not only contain maximal effort, it will also contain all the rides where the cyclist, the athlete will when just out with a friend to drink some coffee. But there will also be some maximal efforts where someone sprinted to the next village or did a maximal effort up a mountain, and it's hard to see. So it's actually not hard to see, but it's hard to filter out the submaximal bits of this data, and that is the challenge that I was trying to solve here. So if we look at so this is showing, it says 4, but I think it's 3 rides, and then plotting the data. Fitting the model to it, and then you see that especially for these shorter durations. Make it a bit bigger. Especially for these shorter durations, the model underestimates what this athlete can actually do. And for some durations, you could say it overestimates, or maybe for these durations, the athlete hasn't done any maximal efforts. So the model fit is a bit of a problem here. It's less so a problem if you have a lot of data. So this is all the data from this athlete that we just saw in the Golden Cheetah OpenData Explorer. But still, there's some bits where the model is, for example, here and here, where the model is underestimating the capability, the fitness of this athlete. And it's very, very easy to see this if you plot the residuals or in this case, the inverse residuals. So this shows how many watts the model, you have this right, how many watts the model is below, above the actual data, the training data. And I hope this makes sense, but what I'm basically trying to do is I want to minimize the area under the curve here. I don't want the model to be under the curve anywhere, because this will mean that the model is fitted to submaximal data. So one approach that I tried here, and if you have any ideas about this, please reach out to me and send your ideas, because I would really like some input here. So what I'm trying to do is do an envelope fit on these MMP curve. And one way I try to do that is doing an initial model fit, then getting rid of all the training data that falls below the fitted model, then do another fit and repeat the process. In this case, after 5 runs, it's a bit hard to see in the plot here. But if we look at the residual plot again, you can see that actually the area under the curve is, well, maybe here there's one bit more. The area under the curve is minimized. So the fitted model is actually fitted quite well to what I think are the maximal efforts. And again, one thing I failed to mention, so in the red dashed line here is the model fit that we saw earlier. So it's this initial prediction, and the black one is the final prediction that was fitted after these 5 runs. So again, to close my talk off, again, I'm repeating this disclaimer that although the model fit that you saw and that I come up with might look good or might even be good statistically, it's still a measure of what has been done and not necessarily of performance. So it's always good to keep that in mind when using power duration models like this. With that, I want to close off my talk. I think I'm a bit over half an hour already. I want to finish off with an open source shout out to some open source projects that have made this talk possible. So first off, of course, Golden Cheetah. the desktop application to analyze your bike rides. Then the Golden Cheetah OpenData project, and a project that I'm a core maintainer of is SweatPy, which is a Python library to do the analysis, and all the analyses that all the plots that you just shown are done using this this library. So if you have any questions or interested in working with me, or if you have any ideas on how I can continue improve on this this power duration model fitting, please reach out to me, or I think there's still a bit of time left to answer some questions here in this virtual meetup. Thanks.
Thank you, Aart. This is very cool, very inspiring. So I know a lot of people are very impressed with the way you're switching with your video behavior and drawing. So the presentation was, and thank you for that.
Nice.
Maybe a bit more on some of the technicalities. There were quite a few questions that came through that some came directly to me, some are more public. One of them was the athlete data that you showed was very biased towards men versus women. Do you know if there's an initiative to change that? And in general, more importantly, how important is that in your particular sphere of work? So any thoughts on that?
Yeah. Yes, it's a very good point, very good question. I think this, well, I'm not conducting any science, but I think in science in this field, in the field of exercise physiology, there's a problem with a lack of female data, to put it like that. And this data set is only an example of that. Yeah. So to be honest, there is no effort at the moment to get more female data into this platform, because we don't have any control of which users are downloading the Golden Cheetah application, and then deciding to actually share their data in this data set. So I think there's, yeah. So if you have any ideas on that, let me know. But I think there's I don't know how we can improve on that. But it is an issue. I think the model that I just showed is very personal. I think there's no generalization done here that could be different for males and females. But I think if you would apply a model like this to a broader group, so trying to fit a power duration model like that over data from multiple athletes, then yeah, I think the lack of data from female athletes is definitely an issue, and you should take that into account when applying these models. Yeah.
Right. Very good. So that answers that. So there was another few interesting questions that came through. Is one of it is, in your experience, how much of what happened before the data is being collected matters? So the idea is, I think most professionals, when they train, especially seriously, they have a training schedule, and depending on when the last time they did sport and how many hours ago, that may or may not impact their performance for the next session. Does that influence your data? Is that something that the data set holds, or is that something you would like to hold? What are your thoughts on that?
Yeah, that's also a very good question. Yeah, that's one of the bigger challenges in monitoring fitness is incorporating the role of the impact of previous activities on the metrics of today. So in this case, I'm thinking what's the application to this. So I think in this case, I'm not too worried about that, because let's say that you did a really hard race yesterday and then did a workout today. The MMP values of today's workout will just drop below the MMP curve and won't be included in the model. But if you want to use this power duration model to predict performance, you certainly have to take into account the training load from the past few days. There are actually there are a lot of ways to do that. I think the best way to handle that is look at the acute chronic work ratio, if I'm correct. So that basically takes an average training load from the past. I think the standard is 42 days, and then take that as a fitness measure, but then also taking the 7-day average training load, and that take that as a fatigue. As a measure of fatigue, and then using those to feed a model, and that way you could predict, maybe use a power duration model like this to predict performance. I hope that explains your question, answers your question.
Yes, thank you very much. And then so Jeroen asked a question here. He says, there also appears to be some correlation structure in the residuals. Do the curve fitting algorithms take this into account?
Sorry, I don't understand that question. Correlation in the residuals?
So I think, so Jeroen is trying to, he would like to see the residuals again. So if you look at the residuals again, this has triggered his attention. So I think Jeroen, you can ask the question. If you unmute yourself, just you, feel free to ask it personally. Or maybe we muted him. So maybe we can take his question offline then, Aart. So
oh yes, I'm here, I think.
Okay, good.
So what I observe is normally when you fit an ordinary linear regression model, you expect the residuals to be independent of each other. So you expect if one's above a certain threshold, then you expect the other one below. Now here there is some, obviously you're working with a time series, right? But you're also working probably with some more complicated correlations in the fact that I can imagine that if you have a peak performance that's quite high, then you may then that may affect your mean maximal power for a different duration. So how do these models take into account this correlation?
Yeah, I'm still not sure if I fully understand your question, but that might be a lack of knowledge on my part. I think I can say that they don't take that into account. So this mean max power curve is basically an expanding moving average. So every point in time is influenced by the point before. So there's of course a correlation in that sense.
Yes.
Does that explain your question?
I'm just interested in the paper as well. So if you could provide a link, then I'll have a look at it.
I'm sure there's a possibility to share some links. Yeah.
And we'll get Aart to go to the matplotlib library. So when we join Meebo in a few minutes, we're going to get Aart to go to the matplotlib, so you can find him in the matplotlib channel. All right. Then maybe just one last question to wrap it up. Aart, is does this fitness model apply to other sports? So this, you seem to do it based on cycling, but this seems a very important aspect for many other sports. Does this methodology and models apply to other sports as well, or is it very much geared towards cycling?
Yeah, that's a cool question. Yeah, so that's a very relevant question. The reason I chose cycling is because cycling is a very lucky sport in the sense that it's very easy to measure power, and power is the intensity or so the power output, and power output is a measure of the work that an athlete delivers over a specific time period. And cycling is one of the few sports where you can do this as easily as as in cycling. I think there are a few other sports where you can do this. I think rowing is one. There's some efforts to do the same in running, but it's more an estimation of power than a real measure of power. So in that sense, cycling is an easy sport to pick for doing power duration modeling like this. But that being said, there are also at least some efforts to do not power duration modeling, but speed duration modeling. So basically doing the same, but then on speed data. To be honest, I'm not completely sure what's the scientific status of these efforts, but I think sort of the same models, the same ideas apply there. I wouldn't say that this omni-domain power duration model will directly apply to the speed duration. Will be applicable as a speed duration model, but maybe some of the underlying theory might. Yeah.